All right, so we're going to go ahead and talk about the natural base functions. These are basically exponential growth and decay functions, except the base is really always the same. It's going to be the natural number, which is the number e. So the number e here is about 2.71828 dot dot dot. It goes on and on and on forever. It's kind of like pi. So we really round that just to about 2.72. And the number e comes from a famous mathematician, Leonhard Euler, and it approaches this, and it kind of goes along with the compounded interest that we're going to talk about at the end of the lesson. So if we look at this equation right here, this is the exponential function. This is y equals a times b to the x minus h plus k. So you notice that it's the same thing, except yesterday when we did this, we had a different number for b. It could be a number that's bigger than 1. It could be a number that was between 0 and 1. Well, the difference is that today we're going to have this number e. The base is always e. So the base is always 2.72. So it's like, well, how are you going to get an exponential decay function if your base is always bigger than 1? And that's where this little r comes into play. That r there, if it's positive or negative, it's going to tell us whether or not we have exponential growth or decay. And I'll kind of talk about that in a little bit. So if r is bigger than 0, if r is positive, if that exponent is positive, then you have a growth function. And kind of think about that. That's saying that you have e to the third power. Well, that's a positive number, 2.72 to the third power. Whereas if r is less than 0, then the function is going to be exponential decay. And think about that. So if I have now e to the negative third power, if we're thinking about properties of exponents, that e to the negative third is going to change this to now 1 over e to the third power. And 1 divided by e to the third power now becomes a decimal. So now we're getting into that decay function, that base that's between 0 and 1. The domain is going to be all real numbers, just like yesterday. So remember, we're going to say that that's from negative infinity to positive infinity. And then just like with exponential growth and decay, your k value is going to be a horizontal asymptote. And then your range is going to be found the exact same way. So your range is going to be from k to infinity if it's positive, and from negative infinity to that asymptote if it's negative. So these last few examples on the bottom of the notes here tell us to use a calculator to evaluate each expression, round to the nearest thousandth. Remember, thousandth is 3 decimal places. So we're really just trying to find that e button on our calculator. And it's going to be the second function of the ln, which is the natural log, something that we'll talk about later in this chapter. So you're going to take e to the fourth, and you're going to type it in your calculator. It's going to look like e with a little exponent. You're going to type in the number 4, and you should get about 54.598. So go ahead and check that, try that, make sure you're typing that in correctly. And then this e to the negative 0.09, you should be able to type that in just like e to the negative 0.09. You don't need that first 0, obviously. And you should get about 0.914. So check that out, make sure you know where that e button is on your calculator. So we're going to be asking you to simplify expressions that involve base e, and all we're going to do is the same thing that we've done with all sorts of properties of exponents. We want to make sure that we have no powers to powers, we want to make sure we have no negative exponents, we want to make sure that we have no multiple bases. So the first thing I'm going to notice is that I have negative 2e to the negative 5x cubed, so I'm going to go ahead and distribute that, and I'm going to take negative 2 to the third power, which is going to give me negative 8, and then I'm going to take negative 5x and multiply that by 3, because of power to a power you multiply your exponents. So my base is going to stay e, and now I'm going to have a negative 15x. And then remember that we can't have any sort of negative exponents, so I'm going to go ahead and move this entire e to the negative 15x into the denominator, because that's the only piece that's negative. The negative 8 is going to stay in the numerator, and then I'll have e to the 15x in the denominator. And that would be my final answer. This next one here, I'm going to go ahead and do the same thing. I'm going to think about maybe simplifying this denominator, noticing that I have 25e to the 6x. Let's rewind for a second, and let's remember how we simplify the square root of x to the 6th. Remember, we broke that up into x cubed and x cubed. just kidding, x squared and x squared. I'm thinking groups of 3 right now. X squared and x squared and x squared is what we broke that up into 3 groups of 2. We chose groups of 2 because this is a square root, which is looking for pairs. So remember, what's really happening is you're dividing 6 divided by 2, and that's telling us that 3 groups are coming out. So as we think about simplifying the square root of 25e to the 6x, we're going to think about simplifying the square root of 25, which is just going to be 5, and then e to the 6x means that how many groups of 2 can you make? You can make 3. So e to the 3x is going to come out of that denominator, that radical, and this is all cubed. So now you have a couple options. You can go ahead and simplify within the parentheses a little bit more if you want to. You can go ahead and distribute. I think most of you would probably distribute, so I'm going to do that. Now I'm going to do a power to power. I'm going to multiply my exponents. So we've got to think we're really multiplying 3 times 5x plus 2. So we've got to distribute that 3 to the 5 and the 2. So now I'll have e to the 15x plus 6. And I have that all over 125, and that 125 is coming from 5 cubed, and then e to the 9x. Now the last thing I'm going to want to do is I'm going to want to think about subtracting my exponents. So I would have 15x plus 6 minus 9x. So think kind of on the side what's happening here. 15x plus 6 minus 9x. Those are my exponents that I'm subtracting. So then the 15x minus the 9x is going to give me 6x. So my final answer here would be e to the 6x plus 6 all over 125. And we can go ahead and leave it like that. We're okay with that. So when you see these problems, you just want to make sure you're remembering all the properties of exponents and you're using those like we did last chapter. Okay, so before we get into graphing, we're going to go ahead and determine whether each function, just from the equation, is going to represent growth or decay, state the domain, range, and the horizontal asymptote. So much the same things that we did in yesterday's lesson. So when we're trying to determine if it's growth or decay, what you need to realize here is that the base in every single one of these problems is going to be e. So 2.72 is always going to be a growth function. So what you have to look at is the exponent, because that exponent is going to tell you whether it's going to stay 2.72 or if it's going to become a fraction. If it's a negative exponent, you're going to flip it and you're going to put 1 over e. So now it's no longer 2.72, now it's a fraction. So looking at our exponents is going to tell us positive or negative if it's growth or decay. So this one here, my exponent is a positive 2x. So because it's positive, that's going to say that this is a growth function. So we can go ahead and write down growth. Now your domain is going to be all real numbers every single time. So we can squeeze in negative infinity to infinity there. Now I always like to find the asymptote first. Your asymptote comes from the k-value. The k-value here is negative 3. So this is y equals negative 3. If we thought about sketching this graph, it's positive and it's growth. So remember, growth starts close on the left side and gets far away, and positive means it's above that asymptote. So technically I have this asymptote here at negative 3. My graph is going to look something like that. So since it's above, that means that that asymptote is the smallest number. So my range is going to go from negative 3 all the way to infinity. Now, if we look at number 6, it says negative 4e to the negative 2x. So now that exponent is negative, so that's telling us that this is decay, because what's really happening is my equation is negative 4, 1 over e to the 2x. Okay, because now that's going to become a positive exponent when you bring it to the denominator. And now 1 divided by e, now that's going to be a fraction. So it's going to become decay. Your domain is all real numbers, so squeeze that in. Your asymptote is going to be at 0 because there's no k-value. You're not adding or subtracting any number to that equation. And then this one, thinking that it's negative, my graph here, and it's decay, so it starts far away and it gets close, and being negative, it's underneath that asymptote. So that means the asymptote is the largest value, the maximum value you can have. So your range is going to be from negative infinity all the way to the asymptote, which is at 0. Now this last one here, the exponent is a positive 1/3, so because the exponent is positive, that's going to tell us that this is growth. Go ahead and say your domain is from negative to positive infinity. Now the asymptote here is going to be at that 5 halves, so we'll say y equals 5 over 2. And then this is a growth function, but it's negative, so that means growth, negative, it's going to go ahead and, here's the asymptote up there, be underneath the asymptote. It's going to be on the bottom. So that means that asymptote is the highest value you can have. So we're going to go from negative infinity to 5/2 for the range.